Let me point out some common mistakes in the topics of derivatives and maximization questions. So first of all, make sure to have a signal when to use the chain rule. So there's a difference between the regular derivative and the chain rule. For instance, when we have ln of x derivative, we know that it's just x, 1 over x. But let's say we have ln of x squared plus 4 derivative. Well, that's 1 over x squared plus 4 times the derivative of x squared plus 4. So whenever we have something more than x, when we have an expression of x, remember to take the derivative of that expression itself. And I did this in previous videos where I showed that there are general derivative rules which we just know how to derive. For instance, e to the power x derivative equals to e to the power of x. X to a power derivative is n times x to the power of n minus 1, and some others. Now, the mental signal is that if instead of x we have an expression, something with x plus 1, x squared plus 4, x to the power of 3, well, we just do the exact same thing, but we differentiate the expression as well. And then, for instance, here, if we have a certain expression to the power of n derivative, same thing. We use the regular derivative property, but we differentiate that expression itself. I hope this helps. Now, let's think about the local maximum and local minimum. What's the criteria to have a local max or a local min? So, let's say we have a function, f of x equals to x cubed plus 2x squared plus 4x minus 16. Now remember, whenever we want to find out a local max or a local min, we need a condition that the derivative with respect to x has to be 0 or undefined. And the reason we can have a derivative that is undefined and it can be a local maximum or a local minimum is the following. Let me show it here. If this would be our graph and this would be our function f of x, which would look, for instance, something like that. This is a local maximum, this is a local maximum, they are peaks. What happens at the peak? It happens that the derivative of our function is equal to 0, so that's one criteria. But look at this peak over here, it's also a local maximum, but the derivative here is undefined, because the slope is increasing and suddenly decreasing, so we cannot have a defined slope, a defined rate of change here, meaning that either of these two have to satisfy. Now, we take the derivative with respect to x and make it 0. Whenever we make the derivative equals to 0, we find the stationary points. We find the points where the graph does not move. It's either on a peak on the top or on the bottom. Now, how do we conclude whether that's a local max or a local min? In my experience, the best thing to do is to put it on a number line. So we put the number line for f derivative of x. We put those points where the function is stationary, where the derivative is equal to 0. So let's say that would be 1 and 3. These are the values for x. And we give values less than 1 on this range, for instance. And let's say we find out a negative value, meaning that the range there until 1 is going to be negative. We give the values between 1 and 3. Let's say it would be positive, and then from 3 onwards it would be negative again. Let me show you how I do it. What I find, that makes sense is that if the derivative is negative here, it means that the function is decreasing. So the function is going down. Then here the derivative is positive, it means that the function starts increasing again, and it becomes negative again, so the function starts decreasing once more. And it visually proves that this is a local min, so this is a local min, and it also visually shows that this is a local max, this is a peak like we have over here, so this would be a local max. Okay, now this concerns the local. If they ask the globals, the global would be just the highest value on the graph. So we compare what is the value of the function there, and then we see which one is literally the highest. Now one common mistake here, one that I was confused about, where do we substitute values let's say less than 1, for instance 0, do we substitute it into the derivative or do we substitute it into the function? And the answer is that we substitute it into the derivative, because we want to know what is the value of the derivative in that range, because the derivative shows how the function behaves. Is it increasing or is it decreasing? So this is a common mistake. Take care not to make it. Now the exact same logic goes with convex and concave functions. Let me go down. With convex and concave functions, recall that we are dealing with the second derivative. So with the second derivative, we just take the first derivative and differentiate it once again. And remember that we have a criteria that when the derivative, the second order derivative, is positive, we have a convex shape, and when the second derivative of x is negative, we have a concave shape. Now how do we solve these ones? With the same logic. We take the second derivative and make it 0. That would be the first step. We take the second derivative of x equals to 0. Now we put it on the number line for x in the second order derivative. Again, we substitute the values in the second order derivative, not in the function itself. And we see, for instance, those points, let's say they were 3 and 6. And we give values less than 3 and we find out the range. Let's say that range into the second order derivatives gives us a negative number. So we have a negative range here, let's say a positive range in between by taking a value between 3 and 6, let's say 4, and then a value higher than 6, let's say 7, and we get a positive range over here too. Now the answer is, or the question is, where is convex? Well, convex is where it is greater than or equal to 0. And because we include the 0, we also have to use the square brackets when we include our answers. That would mean from 3 until, well, positive infinity, because there's no limit over here, meaning that it's convex on the range of 3 to positive infinity. The other question would be, where is it concave? Well, it's concave from the left, from the negative infinity until 3 included. That would be concave. And the other question might be, where are the inflection points? Where the inflection points are the transition between convex to concave or between concave to convex. And in our case, it just means when we have different signs next to each other. 3 would be an inflection point, but 6 is not an inflection point. So it's just 3. Now, what is the takeaway from this derivative question with maximization? When we put values on the number line, remember to substitute it into the derivative that we're working it, not into the function. That's the most common mistake, and please take care with that. So we got these things going on. What else? Let's see with the limits. With limits, keep it very simple. First of all, understand that a limit does not mean equal. Although we write that the limit equals to something, it means that we approach something. It does not mean equal. Limit shows that we approach a value. And first step in solving a limit, let's say x approaches 1, and here we substitute x squared plus 4, is to actually plug in the value into the function. If we approach 1, what does our result approach? It approaches 1 squared plus 4, which is equal to 5. But if we have a limit that gives us an undefined result, so the limit of x approaching 2, and let's say I'd like to have something like 0 over 0, so yeah, can't come up with an example. But the idea is that if we have a result that's 0 over 0, we know that 0 over 0 or infinity over infinity is undefined, which means that we have to use the L'Hopital rule. So we just take the regular limit that we have, let's say limit of x approaching 1. We have our, for instance, numerator, our denominator, and then we take the derivative. And then we take the derivative of each side. And we try to get a certain result. If we still don't get a result, if we still have undefined, well, we execute once more. We take the derivative that we obtained and differentiate it once again. And we keep going until we get a certain result, but make sure to differentiate the upper side and the lower side, not the whole division. That's another common mistake, so take care with that. And one more thing that might be, actually I think Lagrange makes more sense now, but again, what's the method, what's the intuition of Lagrange? Think of it this way: we have the function minus a lambda times our constraint. And how do we do it? The idea is that first of all, we take the stationary points, we differentiate with respect to x and with respect to y, and the reason we do so is because we want to find out a relationship between x and y. So keep this in mind. Look for a relationship between x and y. Let's say x equals to 2y, for instance. If x equals to 2y, and then we have the constraint that x squared plus 2y is equal to 10, well, we can substitute 2y into x, and we would have, for instance, 2y squared plus 2y equals to 10. So we have 4y squared plus 2y equals to 10, and then we can start solving by using the quadratic formula. 4y squared plus 2y minus 10 equals to 0, and we would find out, let's say, 2y values. Let me go to the right because I have no space. We would have 2y values, and because we have 2y values, we need 2x values. So we would have y1, y2. Recall that x in our example is twice as big, so x should be equal, 2 times that. We find x1, x2. This is going to be our stationary points of Lagrange, our critical points, so to speak, that we must check whether they're minimums or maximums, depending on the question. Last thing about Lagrange, remember the interpretation of lambda, that lambda shows how our optimal result, our optimal output, changes with the constraint. Meaning that we have a larger constraint, meaning that we have more available inputs. How much would our maximum optimal output increase? Or on the other hand, given that we have a higher constraint, how much can we reduce our costs? How much can we minimize our optimal costs if the function says to minimize something? And that would be the whole cluster of derivatives and Lagrange and limits. I hope this makes sense, and take away something that you might use where you get confused, so you have like a shortcut, like a signal in the mind to not go wrong. We are done.